Hello everyone, welcome to today's webinar, Interpreting Color Maps. I'm also being joined by Nick DiVincenzo, who is application engineer with Simcenter Test Lab, and he will be your presenter today. So with that, I'll pass it over to Nick and we'll get started.
Okay, thanks Jacqueline, and thanks everyone for joining us. So today we're going to be talking about interpreting color maps and the, type of, kind of diagnoses we can do on rotating machines or other kind of NVH type analysis by using a color map. So to get started, I'm going to show our agenda for today. So I'm going to give a kind of a brief introduction on what a color map is, kind of the data that makes it up. And we'll talk about using color maps to look at things like orders, to diagnose resonance issues. We'll talk about some slightly more specific phenomena in color maps, like sidebands, things you might see if you're analyzing gears, for example, the way transient events show up in color maps. And then we'll also talk about something that's a little more unique in pulse width modulation. So pulse width modulation makes for some, relatively unique color maps. So we've kind of given that a section on its own here, and we'll also discuss it. So without further ado, before we talk about color maps, I just kind of want to reiterate some of the basics here. So a color map is made up of FFTs and frequency data. And so I wanted to highlight that, an FFT is a way that we can decompose a complicated real-world signal into a series of sine waves. And it allows us to troubleshoot maybe what specific component on a machine is causing an issue. We can trace back a component, a frequency to the trouble component. So we'd be using the Fourier Transform to do that. So when we're talking specifically about a color map, a color map is made up of autopowers. So this is the output of an FFT. We have frequency information here and the amplitude of sound pressure. So it tells us at specific frequencies, what sort of sound pressure levels are we seeing, and we can use that to diagnose machinery. If we take multiple FFTs, say we're looking at something, maybe we're sweeping through the operating speed of a machine, we can take multiple FFTs and we can plot them on the same graph. And so here with just this one autopower, we can't see how anything's evolving in time. By looking at this chart or plot on the right, which is called a waterfall, we can see how things are evolving as we increase in RPM. Are there specific RPMs where maybe something is vibrating or there's more noise? Or do we have RPMs where we have good NVH performance, where the thing is quiet or not vibrating? And so a color map is very similar to a waterfall. They're actually showing the same data. All we're doing here is on the left, we have a waterfall plot. If I take this waterfall plot and I rotate the amplitude axis, so in this case it's G's, an acceleration, and I rotate that into the screen or into the page, and then instead of displaying the amplitude with a level in the waterfall, the higher the little bar, the higher the amplitude of that frequency, I'm displaying the amplitude with color. So we have the exact same kind of data here on the left and the right in our waterfall and our color map. Color map is just often a little easier to read. For example, here in this waterfall, it looks like we have a lot of bunched frequency data kind of on the left-hand side here in this lower frequency range. It's kind of difficult to make heads or tails of that because it all looks like it's smeared together. On the color map, it's a little more pronounced. So now let's talk about orders. So one of the things that color maps are often used for is to identify trouble orders when analyzing NVH. So these diagonal lines here, these are called order lines. So as we're increasing in RPM, you can see that this amplitude of vibration, well, I guess not the amplitude, the frequency of that vibration is increasing linearly here with RPM. And so I'm going to take a quick step back, and I'm just going to briefly go through what an order is. And so an order is a vibration or an acoustic response due to a rotating component on a machine. And so if we were just to take a quick example here of an engine, and maybe we've got a microphone next to that engine, we can walk through and look at what kind of frequency content we might see if we were going to take microphone data and analyze this engine. So if we have the shaft rotating at 600 RPM, that frequency is 10 hertz, and maybe the shaft is imbalanced, so we have some sort of vibration each time that the shaft is rotating. And so we might have a 10 hertz vibration at 600 RPM. If we increase the frequency of that shaft, so now we go up to 6,000 RPM, if we convert from RPM to hertz, we would have some sort of amplitude response at 100 hertz. And then we pick a middle speed here as well, and we do the same exercise, and we get some vibration or sound at 55 hertz. And we can plot this on what is essentially a waterfall diagram here. So we can see as we sweep up in RPM, our shaft is vibrating or making noise at a frequency that's directly proportional to this RPM as it increases. As the RPM increases, the frequency of our vibration increases. And so this would be called the first order because we're using this shaft as kind of our reference measurement. If we were going to make this system a little more complicated, say shaft 1 is driving a second smaller shaft, we can do the same exercise. So I'm going to breeze through these slides a little bit and just show the result. But if we plot the vibration of shaft 2 as a function of RPM, we would get another diagonal line on our waterfall plot here. So this would be the third order because the pulley ratio on these shafts is 3:1. So shaft 2 is going to be rotating and responding frequency that is 3 times as high as shaft 1. And so to use kind of a more concrete real-world example, we could look at engine order contents from a combustion engine. So if we're looking at a 4-cylinder, 4-stroke engine, and we want to kind of maybe diagnose some NVH characteristics that we're seeing, one of the most dominant orders here is going to be the second order. And that's because each revolution of this engine or of the crankshaft is going to cause 2 of these cylinders to fire. And because of that, there's going to be an associated sound or vibration with a frequency of twice the crankshaft frequency. So that's going to be second order. An example of how we might see that in a color map is here. So we've got a color map. The x-axis is RPM. This frequency axis here is actually the z-axis, excuse me. And then we've got amplitude on the right and sound pressure. So this might be a microphone at the driver's ear. So I can look at my order content and I can identify this diagonal line here, which corresponds to the second order. And I'll show you that here. This is an active picture. So I can exit out of there. I'll zoom in slightly on my screen and I'll add an order cursor in here. And I'll drag that over here. So this is second order. And we can see that at maybe certain RPMs, the driver is hearing a much louder combustion noise than at other RPMs. So you can use this information to diagnose, what's going on in this RPM range from, 3,000 to 3,500 RPM. Is this an RPM that the vehicle is going to be at during its operating range? And do we need to design some noise or vibration countermeasure to reduce that sound to improve driver comfort? And you can also, I'll drag this cursor along here as well. You can see on the right, that little black box is displaying what order I'm looking at. And you could look and, see what are some of the other dominant orders that we're seeing in this color map, and then use that to identify, the rotating component which is causing your noise or vibration issue. I wanted to also show a way that we can kind of analyze orders actually within Test Lab. So there are 2 things I wanted to show. The first thing is using a live order cursor in Test Lab. So in that active picture, I pulled up an order cursor and I was able to identify, what order each of these diagonal lines corresponded to. But I can also add a processing cursor. So I'm going to add a processing order cursor to my color map. And when I drop that into a front back display here, I get an instant order cut. So I can visualize where the amplitude of this order is highest. And I can also use it to compare 2 orders. So I'll drop another processing cursor in there. And using these cursors, I can kind of instantly compare, okay, I've got 2 high amplitude orders, maybe order 61 and order 110. which one do I think is going to cause the greatest amount of maybe vibration discomfort in my product. Over, what specific RPM. Maybe I'm not concerned with this higher RPM range, so order 60 or 61 is not as big of an issue for me, but maybe I'm going to be spending a lot of time in this lower RPM region where the green curve is the highest, and then I'll know that I need to address the vibration that order 110 is causing. So that's the first thing I wanted to show. And then I also wanted to show, again, on this color map here, I have some ordered data taken, I believe, from a vehicle, and I can see I have this dominant first order here. And so, you can look at this order and, it gives you some insight onto what might be causing the issue. But I can also animate this, and when I animate it, it'll give me some insight maybe onto what specific component of my machine is causing the issue, and maybe give me a better idea of how I want to solve that issue. So if I go to animation here, I have a cab. I've got some data here, so I want to animate some order data, so I'll bring that in here. And if I animate this, I'll maximize this display here. Oops. I can see that this front axle is experiencing a lot of vibration. So maybe this front axle is causing or is resonating, and I can use that to kind of pinpoint what's causing the issue, what's causing my high levels of vibration. And a picture's worth 1,000 words, so it's easier to see here and determine that than it is to look just at that single order on a spectral map. Okay. So in addition to orders, we can determine things like resonances from a color map. So in this color map here, you can see that I've got some diagonal lines. I've got some order content or some high amplitude orders. But I also have this region here on this next slide, I'll highlight it, or these two regions, where regardless of the RPM I'm running this machine at. So, regardless of the RPM of, I guess, my tracking RPM, my first order, I'm seeing high levels of noise or vibration. And so I can determine from this that these are likely resonant frequencies. And so I'll close this out and we'll bring this up as an active picture. I can add a single cursor here. And I can say, okay, it looks like maybe I have a resonance at 440 or so hertz, and maybe I have a resonance at 780 hertz. And so kind of by performing this analysis, you can see, where your product's resonating, and, where you might need to avoid, or what operating range you might need to avoid. If you are going to be spending a lot of time kind of in this region at 430 hertz, you might need to shift the operating range of your product to avoid that. Otherwise, you'll see large amplitudes of noise or vibration. Or you might need to do some sort of structural modification to either shift these resonances either higher, above the operating range, or lower, below that operating range. And so a color map makes these areas of resonances easy to identify. And looking at a color map versus looking at just a 2D display, so something like an auto power, it allows us to see, because we can see how the vibration is changing with time, we're able to see that we actually have a resonance. We might have some high amplitude frequency content, not at that resonance, but just by looking at a 2D display, we can't tell whether or not that's because of a resonance, or maybe it's just because it's the frequency that the whole system is being driven at. But when we look at a color map, it makes those areas of resonance apparent. And so here's just another example. We can see that we have these two horizontal lines. So RPM is now on the x-axis. Frequency is on the z-axis, and we've got amplitude on the y-axis. And so these resonances, there's areas of high amplitude vibration at specific set frequencies, and that does not change as RPM increases. So that's how we identify that these are resonance, or areas of resonance. And we can also do kind of like what I did with that truck example, an operational deflection shape if we have enough accelerometer data on our test object, and you can animate that area of resonance and examine how your test object is going to vibrate and respond at those resonances, and maybe identify areas where your structure needs more support or maybe more fixturing, and that might constrain it and not allow it to vibrate as violently. And so we can look at both of these areas of resonance and kind of look at the operational shapes. So the next thing I wanted to talk about are sidebands, and specifically gear sidebands. And so if I look at a color map, it looks like I have this one high amplitude order in the middle here, where this middle arrow is pointing to. And then it is flanked by two other what look like relatively high amplitude orders. But in this color map, those orders don't correspond to any physical component on our machine. And those orders are caused by irregularities in our gear. And those irregularities, or what we'll call them in this color map, are gear sidebands. And I'll talk a little bit about why we see gear sidebands. So first, I think it's helpful to talk about gear orders. So if we have a gear, this one is a 48 tooth gear spinning at 600 RPM. The frequency of the shaft that it's rotating on is going to be 10 Hertz. So 600 divided by 60. The frequency of the gear mesh is going to be the shaft frequency, so 10 Hertz, times the number of teeth on this gear. So that'll be 480 Hertz. Or if we're just talking about orders, it'll be 48th order, because we'll have 48, kind of bangs when these gear teeth are engaging with each other per one revolution of the gear shaft. And so if we had two gears that were perfect circles and were perfectly meshed, we would just see one order line at 48 Hertz. But, in most cases, we can't make perfectly circular gears. Most gears, just because of tolerances, might be slightly oblong, or maybe in case of a more serious manufacturing issue, you'll have a very kind of accentuated oblong or eccentric gear. And what happens when a gear is not a perfect circle, there is a push and pull apart each time that these gears are completing one full revolution. And so what we're showing on this slide here is, because of this gear's oblong shape, when it's rotating, let's say on this maybe slimmer side up top, gear 2 is going to be more forcibly pushing against gear 1. So it's going to be pushing towards gear 1. And then when we get to this slimmer side of the gear, it's going to be pulling away. So what we get is this kind of twice per revolution pushing and pulling away of gear 2 from gear 1, because gear 2 is not a perfect circle. And that causes a amplitude modulation in our gear mesh frequency. So up top here, we're now talking about a 100th order gear, but we have what the time trace, I guess, of that gear might look like if we had two perfectly circular gears interacting with each other. But because we have this twice per revolution pushing and pulling away from each other, we'll get a second order amplitude modulation of our gear signal. And that would lead to a signal something like this. This is a little more exaggerated for effect, but what is going to happen is then, if we took an FFT of both of these signals, if we have our perfect gears, we'll have just a single peak at our gear mesh frequency for this perfectly circular gear pair. But if we have some amplitude modulation because of this eccentric gear, we will have sidebands off of our main gear mesh frequency. So here we just have one kind of pure tone due to gear mesh. Here we have a peak at our gear mesh frequency, but we also have these sideband peaks at plus or minus second order from our main gear mesh frequency. And again, that's due to this amplitude modulation because of our non-perfectly circular gears. One thing that it might be worth noting is if you look at the amplitudes of these two displays, the perfect gear set has a maximum amplitude of 1G, and the oblong or eccentric gear set has an amplitude of 0.64G. And so eccentric gears are not always the worst thing in the world. Here we have got a plot. We're now talking about a 60-second order gear, but we're still talking about two gears. The blue curve is for a perfectly circular gear set, so we only have one peak at the gear mesh frequency or the gear mesh order. In green, we have a oblong or eccentric gear set, and the green peak here at gear mesh frequency is much lower than the peak of the perfect gear set. So sometimes when you're designing gears, it might be useful to have a slightly oblong or non-perfect gear so we can reduce the frequency content or the amplitude of maybe the acceleration at the main gear mesh frequency. We're spreading out the spectral content over a wider frequency range when we have a modulated gear set, which in some cases will be advantageous. There are some other considerations you might need to take into effect. Eccentric gears won't transmit power as effectively as a perfectly circular pair of gears. But if you're trying to solve an NVH issue, that might be a trade-off that you're willing to make. Another cause of gear sidebands, we talked about oblong or eccentric gears, would be a gear that has an off-center rotation. So here, gear 2 has a misaligned shaft. So it's going to spin slightly off-center, and that's going to cause a first-order amplitude modulation of our gear. And if we look at the frequency spectra again, for our modulated gear set, we're going to have our gear mesh order as dominant, and then we're going to have these plus or minus 1 order sidebands branching off of our gear. And so you can use this information when you're looking at a color map to diagnose maybe some common problems in gear sets. So if you had a really big first order modulation present in your color map, so 1 order off of the gear mesh frequency, that might be an indicator that you have an imbalanced shaft. Maybe your shaft is in the process of failing, or there's a resonance causing that gear to rotate off center. If you have a second order gear sideband or modulation, it could be an indicator that there's a manufacturing issue with the gears that you're using. And you can also kind of, track these things over time and see how the performance of your gearbox changes. So if you take a measurement and you come back and you measure a week later and you see more prominent sidebands, that might mean that something in that gearbox is starting to fail. And there are some other sideband orders present in gear pairs. So this is just kind of a brief overview of different sideband orders that you might see. Okay, so now we'll talk about how transients manifest themselves in color maps and how we can use color maps to analyze transient events. And so we've got this color map here. We've got these high amplitude, very broad in frequency, and as you can see, short in time events. And so these events are transient events. And think back to maybe using an impact hammer for a modal analysis test. When we hit our test object with an impact hammer, we're using an impact hammer because it's a transient event. And transient events tend to be short in time and very broad in frequency. So when we're using an impact hammer, we want to excite as much of the frequency range of interest as possible, which is why we use an impact. So here in this color map, you can see that each of these transients is very broad in frequency. So we've got a lot of frequency content between 1,000 hertz and 3,000 hertz, but really we have frequency content going up to kind of almost 0 to 5,000 hertz. And we can use that, or be aware that that's what a transient looks like, to identify things like, for example, gear rattle or backlash. So I've got an animation here of what gear rattle would look like. So these are two unpowered gears. And so you can see, maybe because of the way that the clearances between the gear teeth is designed, they are allowed to rattle back and forth and impact each other when they're unpowered. And if we look at a color map or an example of that, you can see on the left here, this is a color map of gear rattle. that we have we have frequency content that's very broad in frequency. So we're seeing, very high levels or high amplitudes over a broad frequency range, and that's independent here of RPM, except, independent of RPM. Here we have maybe some rattle that is a little lower in frequency than throughout the rest of the color map. But nonetheless, you can see that this rattling is causing this kind of broadband frequency information that's not changing with RPM. So that might be one way that you could diagnose a potential rattle issue or recognize a potential rattle issue by looking at a color map. On the right, we have a color map caused by gear whine, and this is caused by the power gear set, so loading and unloading of the individual teeth on those gears. And so that would give us frequency information at the gear mesh order, and the frequency of that noise will change with RPM. We can also use color maps to identify things like piston slap. So again, another transient type event. At the bottom here, I have a time trace and the angle domains. You might notice that the x-axis here is in degrees. So this is a time signal from a 4-stroke engine. So it takes two 360-degree revolutions of the crankshaft to complete one cycle. So you can see I go from 0 to 720 degrees. And then at these kind of specific degree increments, I have these big broad transients, which are also showing up here in our color map as a high amplitude, broad, and frequency event. And so you can use a color map like this to identify, okay, where where in my revolution of my crankshaft am I seeing these big transient events, and then maybe relate that back to piston slap or some other disorder in your engine. So now we're going to talk about a slightly more, I think, unique topic, and that's pulse width modulation. And pulse width modulation is a way that you can control the torque and speed of an electric motor with voltage pulses. So it's kind of an efficient way to control an electric motor. And this is becoming, I think, more and more of a topic with the rise of electric vehicles and hybrid electric vehicles. You're seeing more frequency content related to those electric motors. So just kind of as a brief starter, we've got these 2 voltage pulses here, and the frequency of the voltage pulses is slightly different. So we're going to have slightly different content based on, or frequency content based on, the frequency of our voltage pulse. And we'll also have, because these voltage pulses are square waves, harmonics when we take an FFT of this pulse. And so notice here that we can feed our electric motor kind of a variety of different types, or not shapes, but pulses of different widths. And so signal 1 and signal 2 here might be 2 sample pulse trains voltage pulse trains that we would feed an electric motor. Here they actually have the same frequency. So in maybe this 1 second increment here, we're seeing 3 voltage pulses. But signal 2, if this top part of this pulse is the max voltage, maybe 5 volts that we're supplying our motor, signal 2 is supplying voltage more often to our motor than signal 1. And so that'll change the way that our motor handles. So maybe for signal 2, we would be driving our motor at a much faster speed because our voltage pulse is what you would say on more often than signal 1. And based on this pulse width, we'll see kind of different frequency information in our color map, which I'll show in an upcoming slide. But so in addition to supplying our electric motor a voltage pulse, we'll also modulate that pulse with a sine wave to achieve different torque or electric motor speed control characteristics. And so this is where pulse width modulation gets its name from. We're taking this green pulse train up here. This would be called our carrier frequency, and we're modulating it with a sine wave, and we're getting pulses of different lengths. So here, where this sine wave is at a minimum, we're seeing tiny voltage pulse, versus when the sine wave is at a maximum and we've got a pulse that is almost always on and supplying our motor with voltage. And so pulse width modulation produces some pretty unique color maps because we have a carrier frequency here, which in this case isn't evolving in time. So we've got a fixed carrier frequency, and then we've got these harmonics of the carrier frequency, which we call the switching frequencies. And these switching frequencies will depend on our pulse width and how much or how little we are modulating the carrier frequency. And then in one of these color maps, I think this one is an example of a hybrid vehicle. Not only will you get these high frequency pulse width modulation, frequency content, but you'll also see our motor frequency and maybe our firing orders as well. And so these can be used to diagnose different issues in a hybrid electric drive, for example. So here, kind of like I just said, in this lower region of the color map, we have our, what I would call normal or familiar electric motor and combustion engine orders. And then in this higher range here, we have our electric motor control switching frequencies. And so we can look at this, and as you might be able to see, we've got our high amplitude carrier frequency. This carrier frequency might be, if this was data taken at the driver's ear, for example, say for example that carrier frequency is at 5,000 hertz, or a frequency range where the driver's hearing is very sensitive. So we might have a noise issue because the driver is going to be hearing this annoying tonal noise coming from the hybrid electric drive. And as the NVH engineer, we may have to either determine a way to shift this frequency, so you could change the carrier frequency and maybe move it up to a higher frequency where the driver's hearing is less sensitive. So maybe move it up to, instead of 5,000 to 15,000 hertz. But then you'll have to be cognizant of the effect that has on the actual hybrid electric drive performance. You can also see that we can use this to kind of diagnose maybe control issues with our pulse width modulation. So you can see as we increase RPM, we've got our carrier frequency and the switching frequencies, the harmonics or the sidebands coming off that carrier frequency. When we get to a specific RPM, so this looks like it's just over maybe 220 RPM, we change our carrier frequency. And so this might be because we're looking for a different combination of control attributes, different speeds, different torques. And so we shift to a higher carrier frequency in this region. And so you could use this information to diagnose how well you're controlling that electric motor. And then here I've got a zoomed in picture of this red circle region, so you can see a little more clearly maybe that we've got this dominant carrier frequency, which may be the culprit of the noise issue, and then we've got these harmonics coming off of that carrier frequency. And again, to reiterate, those harmonics are due to the way that we're modulating our carrier frequency. So these harmonics will look different based on what our pulse widths are. So the carrier frequency will remain the same. It'll stay here at, for example, 5,000 hertz. But depending on how lightly or heavily we're modulating our carrier frequency, we might see these sidebands or these harmonics shift.